takes 10,000 hours to become an expert, or so they say. It's probably give or take based on your skills level, your genetics, you're born with more superior intelligence, whatever it is. And what you're seeing in this diagram here, in this image, is a spectrum of a maser in a star forming region taken on the 3rd of January 2022. And then if you choose this channel here where the peak is, and you find out at every epoch, at every observation we took, and you find out what its flux was, you plot here, and that creates a time series. And those are two of the most common tools used in spectroscopy. The third is a dynamic spectrum you see up here. And that's when I take these and I stack all of these epochs of observations, the observations that I took every day or every week, whatever, and I stack them up one after another to create this, where the peaks represent the contours. And then, once I've done that, I should be able to see this or that in this. And it takes a lot of staring at this to get that right. And that's what we're going to talk about today. The 10,000 hour rule, what it takes to become a really good observer, really noticing things. That's what we're going to talk about.
The GERA Foundation presents this series called Navigating Research.
This is Malcom Gladwell. He's a mathematician and a famous author. He's the person that they subscribed the quote to, 10,000 hours rule. And largely what he did was he probably processed and analyzed data looking at correlations between hours practiced versus skills obtained in any field or a range of fields. And this is where he came up with this. This is what he's basically going on about here. So, for better or for worse, that's the idea. Remember, 10,000 hours is just a random, it's not a random number, but it's sort of a proficiency level. And I would imagine, depending on what you're talking about, the proficiency level may not be 10,000 hours. It may be 10 hours or 100,000 hours. Who the heck knows? So, it's really the way it goes. Okay, so this is the guy that came up with the quote, the 10,000 hour rule. All well and good to talk about learning and whatnot if you don't retain what you learn, right? So of course there's various techniques and whatnot, and you can see it here. And they talk about the different things. So you sit in lectures, you read books, you watch videos, you do lab demonstration, you have talks with your buddies, you practice out on the field, and or you just learn from others, teaching others. You teach other people. So here they talk about the retention rate. So of course the prize is you start teaching others. And in science in particular, obviously all of this is occurring. You're in lectures, you're listening to people, you're reading the books, and then you're watching, etc. And you're doing lab demonstrations. You do all of this stuff. And then you talk to your buddies, you talk to your professors, you talk to other scientists. And then, of course, the most important thing is you're actually doing it. But when you start teaching others, which they do at universities, you teach classes in physics, you become very good at it. You become very skilled. And as an astronomer, that's the same is also true. So if you stare at data all the time, if you start teaching other people how to stare at data all the time, you become better because you have to be able to explain it. You got to be able to turn that to knowledge that they can understand. So this helps you to retain things. So in other words, if I say I've spent 10,000 hours processing data, I'm very good at it, that's practice effectively. So I'm 75% of my 10,000 hours. That's what they're suggesting. If I spent 10,000 hours teaching others how to process data, it's at a 90% level, things like that. And so when you do all your calculations, you got to take that into consideration. Ain't that entertaining? Although I don't know if I believe some of these things, this idea that this is done by who the hell knows. And I'm just saying, as an example, this is what it might be like. Because some people really could read the cover of a comic book and understand the universe completely, while others could be teaching for 50 years and not really fully understand the topic they're teaching. It's entirely possible that those two opposites occur. So, you got to take it for what it's worth. But I do generally agree that, when you're teaching somebody else, it forces you to teach yourself, to teach them, and it makes you more skilled at it. There's no doubt about that one. You can get caught out badly teaching if you don't know what you're talking about. Maybe it's not a rule. Maybe the correlation that Malcom Gladwell saw was in fact incorrect. And that is possible. Remember, you do things statistically. So you look at large samples of people. But remember, all those people are across a spectrum in terms of intelligence or physical ability, etc., etc., etc. They have different skill sets. And I'm not sure if he actually went and did that first, determined what their skill sets were. So I think what they're saying here, or at least some people have been saying now, is that in fact the 10,000 hours is probably a function of genetic ability. And that makes a lot of sense. I mean, you look at someone like Mozart, or that wrote, whatever the heck he wrote, operas or whatever, at a very young age, 2, 3, 4 years old. I mean, he's skilled. Wayne Gretzky playing hockey was a superstar before he got out of Pee-wees, which is 12 years of age. And yes, they spent lots of hours on the piano or on the ice, but the reality is they were born with an innate gift. Something about them made them better. So maybe they didn't need 10,000 hours to get to the same level that someone like myself might have required, okay, as it relates to astronomy, okay, or sports for that matter. So maybe it's not a rule after all. Maybe it requires revision. And ain't that an entertaining word all the time? Revision. Everything seems to require that, whether it's Newton's theory of gravity that then Einstein then revised, and now people are trying to revise Einstein's. The idea is we're always learning. Isn't that interesting? So it's maybe 10,000 hours for you and I, but it's maybe hundreds of years for the reality to come forward. So maybe it's millions of combined hours of humanity that will get us to the true intelligence that's required to really understand the universe. So it might not be a rule after all, but I still think it's a worthwhile one to carry on holding on to, because the more we practice, the better we get. And in fact, I will quote a famous rugby coach, Bob Dwyer from Australia, and he said, "Perfect practice makes perfect." And that would be true here too. It's no good if you're practicing to do something and you're always screwing it up, or you don't know what the hell you're doing in the first place. So perfect practice makes perfect. So you have to determine the number of perfect hours you've practiced for to get to the skill level you want to get to. Let me step back again and talk about astronomy, okay? And in particular, what I do, which is maser research. I study masers. Massive star-forming regions have these things called masers, and we can measure them using spectroscopic techniques. A spectrogram attached to a telescope in particular. And here's the dynamic spectra of one of them right here in front of you. And I spent 6 years at Hartrail in postdocs, and that worked out to roughly 15,000 hours of practice. Remember that list of things, lecture, reading books, attending seminars, visual, watching videos, etc., 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 all that stuff. Well, I've done all that. Okay, I've done all that. And there'll be 15,000 hours of that in 6 years. So by the time I got on my postdoc, which is the case for most astronomers, you're going to be very, very good. But remember, you have to include all of the things you learned, like maths and science, you learned in public school from grades kindergarten to grade 8, and then in high school from grades 9 to grade 12, and then in undergrad from first year to fourth year, and then your graduate studies, right? Your 5 years of master's and PhD or whatever it is. So you start thinking about that, right? You start thinking how many hours you've actually been learning. And then you've got to expand that beyond to life itself, because things in life mimic the science. Well, it's nature. And nature is the best canvas for study. So things like this, I look at contrails from jet aircraft flying overhead, and I see some of these phenomena that I'm seeing here. And basically, so it gives me some inspiration as to what I'm studying. So after the 6 years at Hartrail, I really became very good specifically at reading these kinds of things, and you start noticing stuff. For instance, up here in the, you see what Joel found, my student, a high school student really, and he found this feature here that is new. It wasn't visible before. It turned on, and not only is it variable, periodic, it also is velocity drifting. So the velocity is no longer 4.8, it's closer to 5 now. And it will likely cross with this feature here. But its period is the same as the period down here, so we know it's in the same source it's attached. That's all well and good. That is interesting. That was kind of cool. But for me, I also noticed up here, look at this this diagram here, you can see there's something weird going on in this very faint blue region. So, of course, I immediately recognize that as very faint maser features. So instead of being 10,000 Janskis, it's probably in the order of 1 to 5 Janskis. These ones up here, and I am correct, it's 1 to 7, I think. Anyways, and I can show that in another data set, which I will do now. Is the same dynamic spectra, but the data is taken from a telescope in Japan, made publicly available. And as I said, I looked up into this feature here, the ones at about 8 kilometers per second, right here, and you can see clearly now they are real. Because they have a much more sensitive telescope, they can see it's very real. So you see two features here, both are periodic, 240 days. Right? And the more surprising thing, and because I've been staring at this thing for a couple years, literally a couple years of staring, I immediately noticed there's something more interesting in the 8.8 kilometer per second feature here. And if you look closely, you see these little ticks in between the big flares. So here's a flare, 240 days, and then you see these little ticks between it. Well, those are flares too. And that was surprising. This is a completely new phenomena, never seen before. You're seeing it first. This video is the first time I'm presenting this beyond 10 other people on the planet. So that's a secondary flare we cannot explain. We think it's a star that's pulsating and it has a non-radial pulsation. So the star is getting bigger and smaller along its axis towards its center, outwards, and the radius is getting bigger and smaller. And then there must be non-radial vibrations on it. And this is the only feature that seems to see those non-radial vibrations. Although we do see some evidence in the second feature here, but not nearly as prevalent as this one here. So I can't prove that's real, but I could certainly prove these are real. So this is new and exciting and interesting, but this is because I've got over 10,000 hours of staring at data to recognize and notice little differences. I've become a very good observer. Maybe not a good astronomer, but a very good observer. And this is what it takes for all of you to become experts in astronomy, to become experts in observing and noticing things, whether it's astronomy or biology or being a good basketball player or a soccer player. I don't care what it is. You got to become very good. It takes thousands upon thousands of hours. And all of that is dependent upon your genetic abilities. Are you born really smart, innately smart, Or have you got the skills of a superstar, you've got, exceptionally fast feet, whatever, or excellent eyesight, whatever the skill is that you already were born with, that will make the number of hours less, and that will make you more likely to become good at it. But I can say this, if you don't practice and know what the hell you're doing in the first place, however much you practice, it's never going to get better. Just never. You got to go out and do a lot of practice. And then it helps to tell other people about it. Because by being able to teach them, like I'm doing right now telling you, I'm helping myself to think about this very carefully, what I'm doing. So all of those things I kind of agree with. But I do think this is a function of genetic ability as well, the 10,000 hours that is. But irrespective, perfect practice makes perfect. Not just slapdash, staring at something. Oh, I stared at it for 2 hours. Meanwhile, you're drunk out of your mind. You're not focused. You're not fixated. You don't have a clear head. No. You got to spend real hours really trying to understand this and look at it in any detail and then studying around that. And then anytime you're looking at things like the night sky, just staring up at the stars, you got to apply what you actually are learning. All those things have to count. Even if you're just looking at the river flowing, after a big storm, you can see the eddies and the currents. All of that will look kind of like this in some ways. And it will help you to better imagine what you're looking at. So the 10,000 hour rule, I think you should all stand by it. I think it behooves you to work your ass off to look at lots of data. Process data. Stare at data. Think about data. And you'll get good at it. And you'll be a bloody good astronomer at the end of it.
The GERA Foundation will produce more videos like this. Please like, share, or subscribe if you enjoyed this video.